Let us now talk about the I2C protocol. I2C stands for Inter-Integrated Circuit Bus. It is a small area network designed to connect several ICs and other electronic systems together. It has been initially created by Philips with the intent of connecting several integrated circuits on a single board, a single PCB. And it was designed using the following specifications. It is a synchronous serial communication that uses two wires to carry information between a number of devices. One wire will be used for data, the other wire will be used for the clock. And today, you can find on the market a wide variety of available ICs that will use an I2C interface, ranging from microcontroller, sensors, memories, LCD chips, and so on and so forth. I2C is used for data transfer between ICs and systems at a relatively low rate. The classic I2C protocol is rated for 100 kilobits per second, and there exist two additional new modes, the fast mode up to 400 kilobits per second, and the high-speed mode 3.4 megabits per second. The main advantage of the I2C protocol is to reduce the board space and cost by allowing the use of ICs with fewer pins and smaller packages, because you only need these two pins to communicate between your microcontroller and your external peripheral. It greatly reduces the interconnect complexity. Again, you only propagate two wires across your chip. And it allows for digital control of many systems that you could use close to their point of use. If we put things in perspective to this class, we are using the I2C control temperature sensor that we did put very close to our edge bridge. The goal being to measure temperature close to the edge bridge, but using a fully digital system to avoid noise problems and so on and so forth. The I2C bus characteristics include both electrical and timing specification, as well as an associated bus protocol. We use two-wire serial data and control bus implemented with two lines, serial data and the serial clock line, SDA and SCL. However, for reliable operation, one should not forget that you need a third line. It is a common ground. In fact, what matters is the potential difference between ground and SDA and ground and SCL. Without a common ground, your I2C protocol will not be reliable. The bus protocol does include a unique start and stop condition to again minimize the complexity or the overhead coming from the protocol, transmission protocol, and you will support an addressing system. Because you have potentially multiple listeners on the bus, you can communicate from one IC to many others. You will have a slave selection protocol using a 7-bit slave address. As a matter of fact, the bus specification does allow an extension of 10 bits. We will look into that later. You also have bidirectional data transfer. You are able to send data from a requester, the master, into the receiver, the slave, or read information back from your slaves. You will have an acknowledgement mechanism after each transferred byte to make sure the transmission is going smoothly. And last but not least, there is no fixed length of transfer associated with this protocol. So you could send several bytes of data from one device to another without knowing by advance how much this length would be. In addition to that, the I2C has a true multi-master capability. What does that mean? It means that any devices with the master capability, obviously, will be able to initiate a transfer on the line. And in order to do that, you need to have additional mechanisms such as clock synchronization and arbitration procedures. The transmission speed is up to 100 kilohertz, as I said, as part of the classic specification, which would be the clock frequency or your SCL signal. And you also have a max line capacitance of 400 picofarads. Why does the spec provide a maximum line capacitance? If your capacitance is too big, you're going to reduce the speed of your data transfer. And that basically approximates to about 4 meters of connections, which is more than enough for board communication. Obviously, that won't allow you to connect multiple boards together or make larger systems, but hey, this is not what I2C is meant for. You also have the capability to allow series resistors for IC protection in order to limit the current going through your various pins. And finally, obviously, the protocol is compatible with different IC technologies because of this notion of bus interconnect and whatnot. An I2C bus will have two types of devices on it: master devices and slave devices. Master devices are capable of initiating a transfer by generating the start and stop conditions. It will take care of generating the clock, transmit the slave address, and determine the direction of your data transfer. The slave, however, will only listen to the bus and will respond only when addressed, which means when the master has transmitted the slave address of that specific slave. Its timing will be controlled by the clock line. The master drives the clock line, the slave will listen and synchronize to it. And as such, one can create these very graceful bus organizations on which you will see one microcontroller, eventually a second microcontroller, both of them having master capabilities, able to take control over the bus. They will connect to several devices using only these SD and SCL lines, and communication will be able to happen from a master to some slave, from a master to another master configured in slave mode, or vice versa. Because the bus supports multi-master and multi-slave communications, you need to have specific hardware connection. In particular, the device must be connected on the bus using an open drain or open collector type of output for both the serial clock and data signal. That way, that will enable a wired OR between the device and avoid any competition between them. All devices do require ground reference, and typically the signal lines will operate between 0 volt and 5 volt. Because you do use an open drain signal, you will need to use pull-up resistors in order to pull back up your signal to VDD. At any given moment, the I2C bus will then be able to be in one of the three modes: idle, nobody is talking on the bus; a master transmit mode, a master has taken control of the bus and is now sending data on this bus; or a master receive mode, the master has initiated a communication and now it released the bus for the slave to provide some answer, to send back information to the master. If we look at the electrical aspects, as I said, every single packages will implement an open drain type of output. In an open drain, let me remind you that only a transistor with the open drain will be connected to the output, which allows this specific transistor to only pull down the node or leave it floating into the Z state. And that way, you will be able to pair several devices on a single and unique line, coupled with a pull-up resistor to make sure you apply a proper signal up to VDD. That way, all the I2C devices are wired OR together, and if any single node writes a 0, the entire line is 0. As a matter of fact, this is a mechanism that is going to be used in the multi-master mode to identify some collision and initiate an arbitration procedure. Start and stop condition. When a master wants to start a communication on the I2C bus, it needs to initiate a start condition. The start condition, same goes for the stop condition by the way, is a transition on the data line, either going down or up, when the clock line is high. All the other transitions that will happen on the data line will happen when the clock line is equal to 0. Only start and stop will have transition when the clock line is high. As I said, both start and stop conditions are generated by the bus master, and the bus will be considered busy after a start condition occurred and until the existence of a stop condition. During the time where the bus is busy, the master will be able to first initiate its transmission by sending the address. The address of a slave is encoded using 7 bits, so each node has a unique 7-bit of address, and most of the peripherals or packages you'll find will have a fixed and or a programmable address portion. if we take the example again of our temperature sensor, a big chunk of the address is fixed, while you have the last 3 LSB's bits that can be selected. That way, you'll be able to connect multiple temperature sensors on the same line, for example. We also have a couple of specific addresses. Addresses starting with 4 zeros or 4 ones do have special functions. For example, when you have only zeros, it is a general code address, meaning that the master is broadcasting some information to all the slaves. However, if it is just starting with 4 zeros and having 1 at the end, is a null address. No slaves should respond to this address. When you start with 4 ones, we are actually triggering the 10 bits address mode, during which the address will actually be sent as part of the next bit. So that way you will send 8 bits of data and being able to take 2 bits of data coming from that specific, the end of this instruction. How does the first byte in data transfer on the I2C line look like? Well, after the start condition was meant, as I said, the master will transmit the address of the slave. So it will generate the 7 bits of the slave address, followed by a read-write bit. This read-write bit will tell the slave what the master is looking for. Is the master looking to transmit data, or is the master looking forward to get data back from the slave? Once this 8th bit has been sent, the bus will be waiting for an acknowledgement bit generated by the slave to confirm that the address has been properly received and that we can proceed further with the communication. Let's actually look more into acknowledgements. The receiver will basically pull the data line low for 1 clock pulse after the reception of a byte. The main idea is that once the master sends the address, the slave that was addressed is supposed to react to say, okay, I actually noted that you want to talk to me, I'm acknowledging that on the line. So for this additional clock period, the data output will be set by the receiver. So if we look at this diagram again, we see what the data output is, or what the various devices are trying to do on the output line. So here on the data output, the transmitter, so the master, is driving the output, but after the receipt of this, at this 9th bit, that's the receiver that is actually pulling down the line. So the master is transmitting data, start bit, 8 bits of address, 7 bits of address, the read and write bit, and then releasing the line while still sending a clock signal for the slave to actually acknowledge that by pulling down the signal. You also have this opposite concept of negative acknowledge, which is when the output, the data line, is actually not asserted by the receiver. So you have this additional clock coming from the master, but the data output is not pulled down by the receiver. This negative acknowledge, also known as NAC, is used in several cases for data transfers. Now, if we look at a more complex case, what can we see? So this is the example of a multi-byte data transfer on the I2C bus. At the very beginning, the master is initiating a start condition right here. This is immediately followed by the 7 bits address, followed by the read-write line. After that, the slave must take control of the line, sending an acknowledgement. Once this is done, the master needs to continue its transfer, and after every single byte of data transmitted, we are waiting for an acknowledgement from the receiver. Once everything has been properly sent, a stop line, a stop condition, is going to be generated by the master, putting back the I2C line on idle. So if we look at a more complex type of system, we will have, when master is writing to slave, start condition followed by the slave address, read write, acknowledgement from the slave, data, acknowledgement, data, not acknowledgement because this is the very last bit of information, and followed by the stop condition. Now looking at the case where a master is reading from a slave, here's what would happen. Again, the master is taking control of the bus, initiating a start condition, sending the slave address, a read-write bit, this time equal to 1 because the I2C master is initiating a read transition. The slave will acknowledge the proper receipt of this information and will then send its first byte of data. The master this time will acknowledge the proper receipt, next byte of data, and so on and so forth until generating a not acknowledgement to indicate that this is the end of the transmission, and the master will then start its stop condition to release the bus line. Now, what happens when a master wants to transmit data to several slave devices? Well, the master could totally decide to initiate and terminate several transmissions, but the master is at risk of being preempted by another master in the middle of its transmission. So in order to do that, let me show you the concept of a repeated start condition. In this example, the master initiates a transmission with a start bit, followed by the slave address, read-write, acknowledgement from the receiver. This is then followed in that case by a standard data receive from for the master. But now, instead of having the master triggering a stop condition, you will be able to trigger another start condition, a repeated start condition, during which the SDA line will go down while the SCA line is high. And that way, after this repeated start condition, the I2C master will send its new address, or the same address as a matter of fact, depending on what you want to do, read-write condition, and then followed by the traditional operations. For example, this kind of mechanism could be used to first send data, or to first read data from the slave and then write data to it, or vice versa. Again, the goal of this repeated start condition is to avoid this master to release the bus and being prevented and being preempted by another master to take control of the bus. Why are I2C interesting? What are the design benefits of I2C? Well, using the I2C protocol in an embedded system is advantageous on many points. First of all, the functional block of your block diagram will actually correspond to actual ICs on your PCB. And that way, it makes things fairly easy to move from a block diagram to a final schematic. If, for example, you want a temperature sensor, you will have a temperature sensor as a clear IC package, and you only need to write a very specific driver for that. You don't need to design specific bus interfaces. Everything will follow the standardized I2C bus interface, all integrated on your chips. You will have a high level, so your protocol will be already implemented as part of the I2C peripheral and drivers. Now, anything you build on top will simply deal with the register specific to your protocol, and you can often reuse the same ICs and libraries in many different applications. So data reuse is maximized. Design time improves as the designer will become quickly familiar with frequently used blocks in your systems. For example, now that you're used to our temperature sensor, every time you'll have to put a temperature sensor, I bet you're going to lose this LM75 because you're used to that. It's very simple and you have accessible to the library. You can remove ICs from a system without affecting any other circuit on the bus. This is interesting, for example, if you're creating several variations of the same PCB. A more complex version will have all the packages in place, while a cheaper, simpler version will remove some of them. Fault diagnosis and debugging are simple. You just need to hook up a logic analyzer to your bus and spoof what's going on. Software development time is reduced by using libraries and reuse. And finally, the simple two-wire bus will minimize the interconnection and will make your PCB design actually simpler.